if we were in free space. So we call the momentum in this function the quasi-momentum because we're not in free space, so it's not in an eigenstate of momentum, but it's in an eigenstate of this thing that's called the quasi-momentum. And the full wave function is the product of these two terms, this phase factor that varies in space in the same way that the phase of a momentum eigenstate would vary in space, and this function that's periodic in space. Now, one of the things that I want to point out is that because of this periodicity in space, there are many different momentum components. And multiplying it by this, this phase factor simply shifts the value of all those momentum components. So for example, if Q is 0, that's the situation that I was showing you here. That's 0 momentum is one of the momentum functions. Plus and minus the reciprocal lattice vector are two of the other components of the momentum wave function. And that would be the same thing here if Q were 0. But if Q is not 0, it just shifts everything over. So that's the function of Q, is it produces a shift on the momentum components, which are the reciprocal lattice vectors. So the block function has momentum components that are the reciprocal lattice vectors, 0, plus or minus a reciprocal lattice vector, plus or minus 2 reciprocal lattice vectors, and then the whole thing is shifted over by the quasi-momentum. That's how one of the ways of understanding this block state. Another thing about the block state is that if I add or subtract a reciprocal lattice vector to this function, it doesn't change anything. Because adding a reciprocal lattice vector just changes the phase of this thing by 2 pi. So I can essentially repeat the whole thing with the addition or subtraction of a reciprocal lattice vector without changing this block state. It's still an eigenstate of the Hamiltonian. Okay, so that's the eigenstates. What about the eigenenergies? Well, here's a picture of the eigenenergies, and you often see this picture at the beginning of condensed matter physics textbooks. The dotted line here is what the energies would be if I were in free space. If I were in free space, the energy is just p squared over 2m. But when I put on a lattice, we open up these band gaps. So this is one of the really important features of physics in a periodic potential, that we have these band gaps, these places in energy that are forbidden. And they occur at the edges of the Brillouin zone, the surfaces that are halfway to the next reciprocal lattice vector. Now, let me just say something about reciprocal lattice vectors and Brillouin zones. The reciprocal lattice vector, remember, is Planck's constant divided by the lattice spacing. Remember, the lattice spacing is half the photon wavelength, half the optical wavelength. That means the reciprocal lattice vector is twice the photon momentum. Okay? So this axis here is in photon momentum. So a reciprocal lattice vector is at 2, and the Brillouin zone, which is halfway to the reciprocal lattice vector, is 1. It corresponds to 1 photon momentum. That's where the edge of the Brillouin zone is. Okay. Now, so now what I want to do is to give you an atomic physicist's picture of where the band gap comes from. When I first studied condensed matter physics as a graduate student, I found this band gap to be rather mysterious. Sure, it's the solution of Schrödinger's equation, but where, how should I understand that there's a forbidden energy? But as an atomic physicist, I can tell you quite easily. So remember that we're allowed to add and subtract reciprocal lattice vector. So that's what I've done here in this diagram. So here's let's look at the dashed lines for a moment. The dashed lines for a free particle, that's the usual parabola that we all know about. And I can just add a reciprocal lattice vector, and it shifts the parabola over here, but it's the same parabola. And I can have more parabolas here and here. There's actually a name for this in condensed matter physics. It's called the repeated zone scheme. Now, let's look at those parabolas. We'll notice that those parabolas cross at the Brillouin zone boundaries. Now you know that in quantum mechanics, whenever two energy curves cross, then if there is any coupling between those two energy states, they will not cross, but instead they will anti-cross. And that's what I've drawn here in the colored lines, is the anti-crossing of those things. And that is what creates the band gap. The band gap in condensed matter systems just comes from an anti-crossing of two otherwise degenerate levels whose degeneracy is lifted by an interaction between the two levels. And what is that interaction? That interaction is known as Bragg scattering. If I have a particle moving in this standing wave, which creates the periodic potential, at a velocity that corresponds to one photon momentum, which puts it at the Brillouin zone boundary, then it can absorb a photon from this laser beam and be stimulated to emit a photon into this laser beam, and it will reverse its velocity, because each of those laser beams gives one photon momentum, and it's now going to change its momentum by two photon momentum, so it's going the other way. And that's the difference between being on this curve and moving to the right, and being on this curve and moving to the left. Those two things have the same quasi-momentum, but they're coupled by absorbing photons from the laser beams. So the reciprocal lattice vector, the thing that represents the change from this curve to that curve, is a change of one reciprocal lattice vector. That's how far we move the parabola over. That reciprocal lattice vector corresponds to the difference in the momentum of the photons of the two laser beams. And it turns out it doesn't matter how complicated your arrangement of laser beams is, it will make a crystal, a lattice, whose reciprocal lattice vectors correspond to the differences between the momentum of the laser beams. So just figure out any lattice you want, figure out what its reciprocal lattice vectors are, and then put the laser beams so that their differences correspond to that, and you'll get that lattice. Okay, so here, what I was showing you here was a cartoon of what the band structure looks like. Here's a real band structure for a lattice that is 5 recoil energies deep. What is a recoil energy? Imagine I had an atom at rest, and it absorbs one photon. It's going to recoil from the momentum of that photon, and its kinetic energy from that recoil is what we call the recoil energy. For sodium atoms, which is what I'm going to be telling you about here, that recoil energy is 25 kilohertz. For, so it's 25 kilohertz times Planck's constant. For rubidium atoms, I think it's 4 kilohertz. 3.5, okay. So it's less because rubidium is heavier and the photon is not as energetic. So, but that's the kind of energy scale we're talking about. It turns out that it's a very modest energy scale. It's easy to make an optical lattice that deep. The thing I want to point out is that even at this extremely modestly deep lattice, you can hardly tell that this used to be a free particle. You can sort of see that there's a parabola there, right? But it's really hard to see that this thing used to be a parabola. The bottom band is practically flat, even at this very modest depth. If we take this up to 14 recoils, the bottom band is completely flat on a scale on which you can see the next couple of bands. So it doesn't take much to put the atoms into a strongly bound condition, one in which the bottom band is essentially flat. Okay, so that's the situation we've got. Now we want to think about how we create atoms in an arbitrary block state. So I showed you before, just turning on a lattice, what happened was it went into a block state that had a quasi-momentum of 0 because the lattice was not moving with respect to the atoms. So the momentum, the quasi-momentum was 0, and that's the block state that I got. But what if I want some different block state, some other quasi-momentum? Well, I could move the atoms relative to the lattice, and that would give me a different quasi-momentum. But it turns out it's easier to move the lattice compared to the atoms. So how do I make the lattice move compared to the atoms? Well, remember remember that if I have two counterpropagating laser beams of the same frequency, that makes a standing wave. It's a standing wave that's at rest in the laboratory frame. Now, let's say that I make one of the laser beams have a different frequency than the other one. So let's say I make this one have a higher frequency than this one. And let's say I move this way. I'm going to see that laser beam, this one, Doppler shifted up, and this one, Doppler shifted down. Let me move at just the right velocity to make it appear to me that this frequency and that frequency are the same. That means in my frame, which is an inertial frame, because I'm moving at a constant velocity, in my frame, I see two laser beams of the same frequency, so in my frame, it's a standing wave, which means in the laboratory frame, it's a standing wave that's moving along at a certain velocity. So all I have to do is change the frequency of one of the laser beams, and I've got a moving standing wave, and if I go into that reference frame, the condensate is moving with the opposite velocity, and therefore has a non-zero quasi-momentum. So we can make any block state that we want. I haven't told you how we get different bands, but we can do that too. We can make any block state that we want. Now, how do different block states move in this lattice? Again, this is something that is well understood from the quantum mechanics of condensed matter, but let's just go through it. The way in which something moves can be characterized by its group velocity. And the general expression for group velocity is that we want to take the derivative of the energy as a function of momentum with respect to momentum. Okay? Now, it works the same way in a lattice where the momentum is quasi-momentum. I just take the derivative of the energy with respect to momentum, and that gives me the group velocity. Let's see how this works. Let's say that we're in free space. If we're in free space, then the energy is q squared over 2m, the usual kinetic energy, right? Take the derivative of that with respect to q, and you get q over m. That's the velocity, right? P over m is the velocity. Okay, so it works just as it's supposed to. Now, what about a deep lattice, where the lattice is so deep that the band is flat? If the band is flat, then that means the derivative is 0. That means that the group velocity is 0. Well, that's just what you expect. If it's a really deep lattice, the atoms are trapped in the lattice, and they're not going to move with respect to the lattice because the lattice is so deep. So this has the right properties that we want. And here's a little cartoon that sort of shows that. If the lattice is strong, then the atoms are just going to be dragged along with the lattice. They're going to have 0 velocity with respect to the lattice. And if the lattice is weak, then it just goes right past the atoms, and the atoms don't notice it, and their velocity with respect to the lattice is just going to be the minus the velocity of the lattice. So if I want to know what the velocity is in the lab frame, I just transform back into the lab frame. Okay, so now that we know all that, we can do an experiment. So in order to give you a feeling of how this experiment works, I've drawn a kind of a cartoon version of the experiment. So in this cartoon version of the experiment, the optical lattice, which can be moved, is represented as a conveyor belt. And I can turn the wheels on this conveyor belt and make it move at whatever velocity I want, and the equivalent of that is just turning the frequency on my laser, which I can do just as easily. Now, the conveyor belt is a little harder to do this, but imagine the conveyor belt has some kind of funny mechanism that allows me to corrugate it at a variable depth. That's just changing the intensity of my laser. Okay? So let's imagine that we start with atoms. The atoms are at 0 velocity, and the belt is at 0 velocity, and the laser beams are off. So there's no lattice. Okay? So they're just there. Now we turn the lattice on, deep. So imagine that my fingers represent the potential of the lattice. The atoms are firmly trapped in between my fingers. Okay? Now I'm going to start moving the lattice. I turn on the wheels of the conveyor belt and I start moving the lattice like this. And I get up to some velocity, and then suddenly I turn the lattice off. What do I expect for the atom's velocity? Well, I expect the atoms to have the velocity of the lattice. Okay, so let's look and see what happens in the actual experiment. So here's the time sequence of the experiment. I Start off with no lattice and no velocity of that no lattice. I turn on the lattice. When I get it on, then I start moving it. When I get it up to the velocity I want, I turn the lattice off. I wait a little while. I take a picture of where the atoms are, and that tells me what the atom's momentum is. You've already seen what happens when the lattice isn't moving. I get a diffraction pattern, and the average of the velocity of these atoms, this is momentum in this direction, and number of atoms is the brightness of that spot. The average is 0, as you expect. As I change the velocity of the lattice, what happens is the average moves with the lattice, just as you expect. The atoms are dragged by the lattice, and when I turn the lattice off suddenly, I see the average velocity of the atoms is equal to the velocity of the lattice. Okay, so that's easy. Now let's look at a slightly different problem, almost the same problem. I'm going to start with the atoms at rest and the lattice at rest and the lattice off. I'm going to turn the lattice on. I'm going to accelerate the lattice up to some velocity, and while it is at that constant velocity, I'm going to slowly turn down the lattice, turning it off adiabatically. In the previous experiment, I turned it off suddenly, diabatically. Now I'm going to turn it off adiabatically. And I want you to tell me what will be the velocity of the atoms. And it's a multiple choice test. So the first answer is, will it be the velocity of the lattice? How many people think it's going to be the velocity of the lattice? Just like before. You people have taken too many multiple choice tests. You think I'm trying to trick you, right? Okay. So we had a few votes for the velocity of the lattice. How many people think it's going to be 0? 0 is a nice round number. How many people think it's 0? A few, maybe even a few more for 0 than the velocity of the lattice. Okay. How many people think it will be somewhere in between? About the same. Maybe a little bit more for that. Okay. How many don't know? Okay, that seems to be so far the plurality. How many believe it's none of the above? Okay, we've got at least one vote for none of the above. Now, one of the things I want to remind you of, this is a simple problem in condensed matter physics. It's especially simple because this is what we call a single particle problem. There's no interaction between the atoms. I'm going to get the same answer if I've got one atom or if I have a million atoms if they don't interact with each other. So this is the kind of problem that everybody says is an easy problem, but you don't know the answer. And we didn't either when we first thought about this experiment. And of course, once we did it and figured out what was going on, it was easy, as every problem is easy once you know the answer, right? But we didn't know the answer either. So let me show you. So this is just remembering what happens. You first turn the lattice on, then when it's on, you slowly ramp up the velocity. You keep the velocity constant while turning the lattice off. And this is what happens. When the velocity of the lattice is less than a velocity that corresponds to the edge of the Brillouin zone, then the final velocity of the atoms is 0. 0. Don't these atoms know about Newton's law? Don't they know they're being dragged along at a non-zero velocity and you turn the lattice off and they stop? But if you exceed the velocity that corresponds to the edge of the Brillouin zone by just a little bit, when you turn the lattice off, they'll be moving twice as fast. And they'll be moving that fast until you get to the edge of the next Brillouin zone, where suddenly their velocity will jump by another reciprocal lattice vector. What is going on? So here's our cartoon of the optical lattice. The dashed lines are, as always, the free particle dispersion curve, and the red lines are our cartoon of what the band structure looks like for our lattice, which is not so deep in this cartoon. But let's think about what happens. We start with the atoms here at 0 quasi-momentum. Now we're going to stay in the lattice frame, and we're going to accelerate the lattice. That means in the lattice frame, because we're accelerating the lattice, there's a force. The opposite direction of the acceleration, an inertial force, and that force is accelerating our atoms. So the atoms are being accelerated, and they accelerate just like anything else does. F equals ma, where a is the rate of change of the quasi-momentum. So they just accelerate along and change from having zero quasi-momentum, having some non-zero quasi-momentum. Now let's say we get up here, close to the edge of the Brillouin zone. The atoms are in the lattice, they have this non-zero quasi-momentum. Now what we're going to do is we're going to slowly turn the lattice off. That means we go from the red curve adiabatically to the dashed curve. Now the dashed curve, remember, is in the moving frame of the lattice. It shows an atom moving at some velocity with respect to the lattice, but that velocity that it's moving at with respect to the lattice is the velocity corresponding to the quasi-momentum given by whatever the velocity of the lattice is. When I transform back into the lab frame, the velocity is zero. On the other hand, if I go over the edge of the Brillouin zone, that means on this side of this crossing, then I'm on this red curve, and when I adiabatically turn things off, I'm on this curve. And this curve is obviously an atom moving in the opposite direction from one here, and now when I transform back into the lab frame, that atom is moving with two photon recoils, which is to say a reciprocal lattice vector. So we can understand this whole process just from this simple band structure picture, but it's not the sort of thing you ever think about doing in condensed matter, because this isn't the kind of experiment you do in condensed matter, but it's the kind of experiment that's easy for us to do in atomic physics. In fact, it's closely related to an old idea in condensed matter, which turns out to be very difficult to achieve, known as block oscillations. What are block oscillations? Let's now imagine this is actually a crystal lattice with electrons, and I turn on an electric field. So I start off my electrons at zero velocity. I turn on the electric field, they accelerate. Just like what happens with in the frame of the lattice with my accelerating lattice. The atoms, the electrons accelerate until they reach a momentum that corresponds to the edge of the Brillouin zone. At the edge of the Brillouin zone, they satisfy the condition for Bragg scattering. Remember? The electrons are seeing periodic potential. If they have the right velocity, they will Bragg scatter from the lattice. When they Bragg scatter from the lattice, they reverse their momentum. So these atoms that are here have their momentum reversed, they're over here. And then they get accelerated again, and they have their momentum reversed, so they go over here, and they get accelerated again. Now I want to emphasize this process of going here, Bragg scattering, going to the other edge of the Brillouin zone because they reverse their velocity, and then being accelerated again is exactly the same thing as going here and just continuing like this. Okay, it's exactly the same thing because all these repeated zones are just the same thing all over again. All the physics is in this first Brillouin zone, which is often called what do they call that? The collapse zone scheme, or I forget. There's a name for it in condensed matter physics. Reduced zone scheme, thank you. Okay, so that process that I've just described, where the electron is accelerated to the edge of the Brillouin zone and then Bragg scatters, is the process known as block oscillations. So if this were to happen, it would mean that the electrons would go nowhere. And if this block oscillation were to happen, then conductors would not conduct electricity. But that's not what happens. What happens is that the electrons scatter from phonons and impurities and defects, and it messes up this process, and we get ohmic conduction. But if you had a perfect lattice, you would get block oscillations instead. Very difficult to see in condensed matter systems. Recently, people have done it with superlattices, but it's very hard to do. It's something we do to warm up before lunch with cold atoms, because it's one of the most standard things that one could do. So this is one example of how we can do things because of the different kinds of control and measurement that we have, and because of the purity of our system, we can do things that are well known in condensed matter physics, but really hard to do. So here's just a way of illustrating that whole thing about Bloch oscillations. This is the picture you saw before. If we go into the lattice frame, which is where you would see the Bloch oscillations, these things transform into these oscillatory velocities as a function of the lattice velocity. So that would be what Bloch oscillators are. If I put on a constant acceleration, then the electrons are just going to oscillate back and forth and not go anywhere. And that's exactly what happens to our atoms, but that's not what happens in general to electrons in the solid. Okay, so now, the story that I've told you so far illustrates how we can get surprising results with atoms and optical lattices and behavior that isn't easy to see, but that's not the real fun part. The real fun part is when we turn on the interactions. And we're getting late, so I'm going to do this a little bit quickly, I think. Although, well, it says there's 8 minutes left. That's not a lot of time. But let's talk about interactions. I'm not going to talk about any of that stuff, although it's beautiful. It shows how using interactions we can map out the Brillouin zones. We can make pictures of the Brillouin zones with our atoms. But I'm not going to do that. Let me talk about this instead, the mod insulator transition. We heard a little bit about this on Monday, those of you who were here for the talks on Monday. So the idea here is that there is a phase transition that was figured out by Mott, where a system that is interacting in a very simple way transforms from being a conductor to an insulator. And here's the physics behind it. The physics behind it is called the Hubbard model. Here I'm calling it the Bose-Hubbard model because of the fact that the particles are bosons. But originally, the Hubbard model meant for fermions. But the idea is you've got a periodic potential, and there's a tunneling rate to go from one lattice site to the other, and there's an energy cost to have two particles on the same site. And those are the only things that go into the theory. You don't put anything else in. So it's an extremely simple theory, just the tunneling rate and the energy cost to have two atoms on the same site. And you can show that, and Matthew and Daniel Fisher and their colleagues did show this a little while ago, that there's a phase diagram that results from this, where the superfluid phase, or the conducting phase, is what happens when the tunneling is much bigger than the energy of the on-site interaction. And then the atoms just occupy the whole space as any Bose gas would as a superfluid. On the other hand, if the tunneling is very much less than the on-site interaction, then the lowest energy configuration is for every atom to be localized on one lattice site and not to explore all the other lattice sites where it would interact with the other atoms and cost energy. Instead, every atom sits on the lattice site, and if there's the same number of atoms as lattice sites, then we have just one atom per lattice site. Now, the fact that we know exactly how many atoms there are in a lattice site means we may not know, we are not allowed to have any understanding of what the phase, what the quantum mechanical phase of this wave function is, because there's a number phase conjugate relationship. So remember when we divided our condensate up into a bunch of mini condensates, I said they all have the same phase. That meant that I didn't know how many atoms were on there. There had to be a fluctuation. Here, I know exactly how many atoms there are on each lattice site, and so I cannot know what the phase is. And that feature allows me to tell which of these situations I'm in. So here is a situation where I've got the superfluid phase, where the atoms are spread out, occupying all of the lattice, and then I see a diffraction pattern. And as I make the lattice deeper, I get to the place where they're well localized, and then there's no diffraction at all, and the diffraction disappears. So this is the insulator phase, this is the superfluid phase, and by looking at these point-like structures, we can see exactly when you make the transition to not having any superfluid anymore,